Hello, this is Steve Barfield with Siglent Technologies, and I wanted to talk just a few minutes today about digital storage oscilloscopes, or DSOs, and the FFT function, the spectrum analyzer, or fast Fourier transform, as it's known. We've had several people ask us about using the FFT feature of a DSO at low frequencies. And by low, I mean under 1 kilohertz or sometimes even higher than that. But let's try 60 hertz today. It can be done. It's not that hard. It is a little counterintuitive, perhaps, but it works just fine, particularly with modern oscilloscopes. So what we'll do is we'll start with just your basic 60 hertz sine wave here, and that's all we're going to do. It's 1 volt peak to peak, and we're going to go straight into the oscilloscope, and it looks as we expect. Now, what happens? Let's zoom in just a little bit. What happens if we add the FFT function? And you'll see there on the bottom of the screen, we've got our 60 hertz response, but it's so far compressed to the right side of the screen that it doesn't do a whole lot of good. Well, what about if we sped up the sweep speed? That's kind of a way people tend to zoom in. So we'll speed up the sweep speed. You can see it there in the time domain speeding up. But it's not only not improving, it's actually getting worse in the frequency domain. So that's not doing us any good. Well, if speeding up the sweep or reducing the sweep speed makes it worse, then perhaps reducing the sweep speed, going the opposite way, will make it appear better in the time domain, the frequency domain. I went over the roll there. And sure enough, that is what happened. You can see the fundamental, that sine wave, 60 hertz, did come out a little bit from the edge of the screen. Still not real usable, but let's see if we can improve on that some. Well, this scope has a adjustable hertz per division here. You see we're looking at 250 hertz per division. But if we're looking at a 60 hertz sine wave, obviously we need to probably get in closer. So let's choose that, and let's see what happens here. We'll jump down to, there's 125, and sure enough, it moved over away from the left edge there some. And we can actually go down lower. There's 50 hertz per division. And there's even 25 hertz per division. So that certainly is a nice amount of resolution. We'll go back to 50. And we could work with that. So that's, by the way, we also were set at 10 dBV, 10 dB per division. And we can adjust the position here if we like, as you'll see. So we could change that vertical scale as well and get more dynamic range. Now, let's use a little more realistic example. So instead of the sine wave, let's go to a square wave so we can get some nice harmonics here. And sure enough, there we go. So that should be a 60 hertz fundamental with odd harmonics going for quite a while. Let's turn on the cursor just to verify that, and let's change this over to math. Okay, and sure enough, as we move the cursor, we can see it's right smack on 60 hertz. If it'll focus, which it won't, and there it is. And that, if we look at our first harmonic that appears, that should be the third harmonic of 60 hertz. That would be 180, and I scroll too fast. 180 hertz, which is what we get there on the screen. So it's operating just as we expected. If we wanted to, we could even go down to, instead of 60 hertz, we could back it down to 30 hertz. And we still get good resolution there on a screen. That is on the 50 hertz per division. Again, we can improve that by choosing the right control down to 25 hertz per division. So there you can see at a 30 hertz signal, we've got excellent resolution. We can change our window type or filter type, the IF filter, to get better frequency resolution. But really, it's no problem to do that. If you've got any questions, please contact us at info@siglent.com. Again, that's info@siglent.com.